Okay, what is there some homework problems we should talk about?
51.
51? Has been suggested. 46, 51. What other suggestions? What's that? 49? Can I see your book? I left mine at home. 46.
46 and 47 are what you gave us.
41, 51. Okay, so of 46 and 47, is 46 the one to do?
I think so. It was a
47 goes a step further.
47 went a step further.
Yeah, so you would
Let's take a vote. All in favor of 46? All in favor of 47? It's about the same. And what about the rest of you? Got it. Doesn't matter. One more time. All in favor of 46? All in favor of 47? Oh, there's more of you. 47. Okay, so we'll do 47, and then 49 and 51 have been suggested. Oh, we didn't actually define amplitude yet. Okay, so we'll do this. So let's and then let's do 49, and 51 won't be graded. I guess there's some terminology we didn't cover yet in 51. Okay, we'll cover that today. So we'll go over 47 and 49. So go ahead and turn in what you got. Remember, you're also turning in the work from the handout Wednesday. Yeah, yeah. If you included it, yeah, sure. I said to do it on separate paper. Yeah. Yeah. Just write out the solutions. That's right. So what did we decide to do? 49 and 47 and 49.
Is that what she said? No.
I really did.
Yeah.
Okay, 47. Okay, there's a lot to it, so I'm going to just roll, okay? I'm going to go fast. If you want to stop me, I'll leave it up to you to stop me. Okay, so you've got the 1.3 meter string. The ball is flying in a circle like this. Plane is perpendicular to the ground. Counterclockwise from the 3 o'clock position. Situation, illustrate the quantities, starting point of the ball. So, sketch might look like this. Here's the string, starting point. Here's the ball. Okay, and then it's going this way, counterclockwise. And we could, this is, the radius is 1.3. Okay, and then the angle that it goes is, let's say theta. So that's a little sketch of what's happening here. All right, a function that relates the horizontal distance to the right Is it in meters or measured in meters? Okay, so horizontal distance to the right. Which function is that? That's our cosine function. And then just the cosine outputs what to the right? Number of radius lengths, but this is asking for meters. So it would be 1.3 cosine theta. Questions on A and B? So that's pretty basic. Okay, C. 1 revolution takes 0.7 seconds. Okay, how could we find revolutions per second? Or, I'm sorry, radians per second. So 1 revolution then is how many radians? 1 revolution is 2 pi radians. And that's how many seconds? 0.7 seconds. So all these numbers correspond. Different units, but they're all kind of equivalent. 1 revolution is equivalent to 2 pi radians, is equivalent to 0.7 seconds. So if we want meters per second, we have the number of seconds. So how many meters does it travel in that many seconds? How many meters? So another equivalent. So what's the arc length of 1 revolution? Yeah, 2 pi times the radius, 1.3. That would be meters. And so this number of meters corresponds to this number of seconds, and that's how we can get meters per second. Whatever that turns out to be. That would be the speed as it's meters around the arc per second. Okay? Radians per second. So that would just be 2 pi over 0.7. So 2 pi over 0.7 would be your radians per second. Meters per second would be your total meters divided by 0.7. Okay. Are we on D now? Formula that relates the distance the ball traveled in meters in terms of the number of seconds n since the ball began to move. Okay, so we got a couple different things going. This is kind of a jump here. It's a couple different things. So if the input is n, the distance the ball has traveled in meters. So d is like arc length, right? And what was how do we get arc length? It'll be number of radius lengths, which is theta, times how many, the length of each radius, which is 1.3. Okay, so this would be how many radius lengths it goes around, and this is the length of each radius. So this would be in meters, but we want it in terms of the number of seconds. Yeah. Mm-hmm. Yep. Right, because this is how many radius lengths around the arc it goes, and then this is the length of each radius length. So this would make it meters, but we want it in terms of n, the number of seconds. So how many, so that means we have to write theta in terms of n. So what angle does it sweep in 1 second? Do we know that? We know that in 0.07 seconds, it sweeps 2 pi radians. Okay? And in 1 second, it sweeps how many radians per second? It would be 2 pi over 0.7. Let's leave it that way. So then in n seconds, how many radians does it sweep? That's So this is how many radians it sweeps in 1 second. So how many will it sweep in 2 seconds? Twice as many, right? In 3 seconds, 3 times as many. So in n seconds, it'll sweep 2 pi over 0.7 n. So this is theta in terms of the number of seconds that goes by. So it would be 2 pi over 0.7 n times 1.3. All right, so there's a lot going on there. Let me make sure you understand it. Did you follow everything? I was making a little table here of number of seconds and corresponding angle theta. So we know in 0.7 seconds it goes 2 pi. We know in 1 second that would be how many radians per second it goes, which would be 2 pi over 0.7. So then in 2 seconds it would go twice the angle. In 4 seconds it would go 4 times the angle. So in n seconds it would go n times how far it goes in 1 second. So that's theta in terms of n. And so from this up here, then we take that theta times 1.3 will give us the distance in meters after n seconds. Anybody have a question on that? Does it make sense? Okay? Define a formula that relates the measure of the angle in terms of the number of seconds. Well, we had to do that to get this one. We already did it, right? To measure the angle in terms of the number of seconds. That's our 2 pi over 0.7 all times n. We already did that. Define a function g, horizontal distance to the right of the vertical line as a function of seconds in meters, okay? So it's going to be g of n, right? G of n. So will it be a cosine or sine function? No question. Yep. So what was your, yes. So maybe I went the long way around. So how do we get meters per second? Yeah, so you could do 1.3 meters times 2 pi divided by 0.7 seconds. Yeah, so meters per, that's how many meters you go in a second. So you go this many meters in n seconds. So there's your, it all should turn out to be the exact same thing. Does it turn out to be the same thing? 2 pi, 1.3 in the numerator, 0.7 in the denominator. Yeah, so it turns out to be the exact same thing, but yes. So either approach. So I did radians per second, and then times the length of each radius. You did meters per second times n, which is both give you the same thing. Yeah. Okay, so gn. We want the horizontal distance to the right. Which function is that? That's our cosine. Do we want meters or radius lengths? Meters. So if we want meters, what will we do to the cosine function to get meters to the right? Multiply by the 1.3. Okay, and we want what goes into the parentheses. What kind of quantity will go into the parentheses? She said angle measure. Agree with that? Angle measure goes in, but we want that to be in terms of n. So what is our theta in terms of n? It's that thing we found right there. So if you take this right here, that's theta, and that's what cosine accepts. Its function is to take theta and give you horizontal distance to the right. Here's theta in terms of n, and so we can put it, cosine will accept that. And then cosine will give you number of radius lengths to the right. Each radius is 1.3, so we're going to multiply that fraction of the radius times 1.3 to get meters. All right, sketch F. We're going to sketch F. So when we sketch F, I'll do it down here. What about let's do the horizontal axis first. How will we figure out how to do the horizontal axis in this case? It's based on what quantity? Time, n seconds. So we want to come up with one full cycle. What's one full cycle in seconds? 0.7. So what do? We did last time in class that will help us to sketch this. Yeah, break it up into? Yeah, so divide 0.7 by 4 because one cycle for the sine and cosine nicely breaks up into 4 pieces, right? So what's 0.7 divided by 4? 0.175. So we get 0.175. Halfway is 0.35. And then 0.525? Is that right? Can you read that? How did I do? So break it up into 4 pieces. What about the vertical axis? Yeah, so in meters, the furthest it can go to the right is 1.3 meters. The furthest it can go to the left is also 1.3. That's our negative 1.3. So at time equals 0, where is it to the right? How many meters left or right is it at time equals 0? He wants at 1.3. Yep. And we know that's what our cosine is. Cosine starts at the maximum. In the first quarter cycle, cosine goes to 0. So remember, we're going around the circle here. And then in the second quarter, the distance to the right goes to negative 1 radius length or negative 1.3. In the third quarter, what's the distance to the right? Back up to 0. Vertical, so distance to the right is 0 here, right? And then in the last quarter, distance to the right at the end, 1 radius length or 1.3 meters. So these scales are really important. So meters from negative 1.3 to 1.3. And then break your period in seconds up into 4 equal pieces to get those 4 pieces of the graph. Okay, so H is just, now we're doing 0.25 radians per second. If you're just going to, it'll be this same thing, but you're going to be changing what happens in here. Oh, is the radius different now? It's still measured in meters to the right, same one. Okay, questions on 47? Does it help? So it's putting everything together now. It's like everything we've learned in trig. You have to apply all together. Oh, you want to do H? Okay, let's do H. Questions on, so H is kind of a new problem. So questions on A through G. All right, can I erase it? Okay, so H, if we sweep out 0.25 radians per second, we want the function that relates the horizontal distance, again, will be what kind of function? Cosine? Meters or radius lengths? Meters, 1.3 still, right? Let's try that again. This could be 1.3 cosine. Question is, of what? What goes in the parentheses? Angle measure. So it's, we want, this is G or J. J of number of seconds. Let's call it T this time. So what do we need? We need the angle measure in terms of T. Yeah, If you're ever not sure, just make a table how those two quantities are related. After 0 seconds, how many radians? 1 second. 0.25. 3 seconds. 0.75. T seconds. After T seconds, how many radians has it gone? 0.25 T. Every second, it goes a quarter radian. So in T seconds, it's going to go T quarter radians. T quarter radians, 0.25 T. So that's our theta. So we can just put it right in here, 0.25 T. Over what time interval did the ball complete one revolution? How do you know? So we got this angle, and we want one revolution. So what are we going to set that angle equal to? 2 pi. So we want the time t such that that angle will then equal 2 pi. So you want the time t that that angle will equal 2 pi. So t is going to be 2 pi over 0.25 or, sorry Corey, you were incorrect, 8 pi seconds. How many seconds is that? So if you can do that, if you can swing a ball perfectly in a circle so it'll take 25 seconds to get around, you can have an A in the course. So think about what the numbers mean sometimes, or all the time, okay? This is saying around 25 seconds it would take to swing the ball around in a circle. So can you imagine this? You think I'm boring, right? That would be boring, right? So it's impossible, though. So the ball would be like defying gravity. It would take 25 seconds to get around. So not a great question. Wasn't well thought out because it's kind of a physically impossible thing to do. Maybe 25 radians a second, okay? Or 2.5 radians a second is a little bit better. But maybe 25 radians a second. All right, questions on 27 or 47? Okay, 49. So when we get started with these, the bike tire is really helpful. So basically here, let me set up the situation. So what we're saying that this is like the pedal. So what does this function mean for the pedal? And this is like the tire valve. So by relating it to this physical example, we can really make heads or tails of how these two functions relate to each other. Okay? So what is this function describing of the pedal? So if it's just f of theta equals sine theta. Where am I here? There it is. Okay, so the function is f of theta equals sine theta. So that particular function, what would it be monitoring, or what quantities would it be relating to the pedal? Okay, yeah, vertical distance measured in what units? In radius lengths. Okay, so what would the maximum of that function be? What's the maximum radius lengths that can get? 1 at the top, right? And -1 at the bottom. What about the input? The angle measure, okay? So this function would give us the height above the horizontal in radius lengths for an angle swept out theta. All right, what's the other function? What's it called? H of theta is So, what does this output? So if this relates to the tire valve, then what is that giving us? It's the output of that function. No, the output of this function. What's that? Radius lengths as well? What radius lengths? So what quantity? Vertical distance and radius lengths again. So it's going to be the vertical distance and radius lengths of the valve. But how is the valve turning relative to the pedal? So as the pedal turns, how much does the valve turn? So if I do one full rotation of the pedal, what will the valve do? If I do one full rotation of the pedal, what does the valve do? Goes 1/4 that angle. If I do another full rotation, where will it end up? Now it's done 2/4 or halfway around. So when you see these two, you think the angle here, the input angle is 1/4 what the input angle is here. So you imagine what the valve would do relative to the pedal to make sense of it. It's going to make 1/4 of the angle that the pedal does. You go around again, another quarter. So 2 times around the pedal gets you halfway around with the valve. So what does that mean for the graph? So the sine graph will start where? At 0 or 1? And in one rotation, it'll do one cycle, which is 2 pi. How much of the cycle does the tire valve do when theta goes from 0 to 2 pi? Yeah. So the question is, what will the period of this be? The period will be pi over 2? So in one full rotation of theta, how much of a rotation do we get of the tire valve? 1/4 as much. Therefore, the period for the tire valve is going to be 4 times as much, or 8 pi. I can only show half of that. So here I'm showing 2 rotations of theta only gets us half of the period of h. So we would need 4 rotations, or 8 pi, to get 1 period, 1 rotation of h. Make sense? So if the angle's spinning 1/4 as fast, the period is, therefore, what? 4 times as long. 4 times as long. So if we understand all that, we should be able to answer any question they throw at us here. How much does theta vary? Nope. How much does theta vary? How much does theta vary by as theta over 4 varies by 2 pi? So what happened as theta over 4 varied by 2 pi? How much does theta vary? So that's saying a period. That's saying a period of the h function. This is saying 1 period of the h function corresponds to 8 pi of h. 8 pi of f. Right? So by saying theta over 4 is corresponding to 2 pi, we're saying that yeah, so it's 1 full period of that quantity theta over 4. This is saying 1 full period. And we saw that 1 full period meant 4 periods of f, or 8 pi. Period of h. We already got 8 pi. How does the graph of h compare with the graph of f? Is it scrunched up or stretched out? Stretched out times 4, right? So if that's period is 4 times the stretch. Okay. Put everything away. Here we are. Okay, so question was, what quantity relative to the fan? So we know seconds, obviously time's going by, so this feet quantity. What quantity of feet might the graph be modeling about this fan? Okay, so he's looking and he's saying that the fan blades, the length of the fan blades are about what? 2.5 feet? Is that how long the fan blades are? Yeah, it's the radius of the circle, 2.5 feet. Okay, but what quantity does this graph show about the fan? What? She wants vertical distance above the horizontal diameter. Where is the horizontal diameter here? What's that? No, the graph is, so I'm asking you what quantity about that, like what quantity relative to the fan might the graph be showing? Well, I didn't tell you it was from the floor. I said, here's the graph. What quantity relative to the fan is that graph displaying? The quantity. What quantity? What's that? Horizontal distance or vertical distance? Okay, if we start at 3 o'clock position, it'd be vertical distance. Vertical distance from what? From the floor? No, have to be from the horizontal diameter. So it'd be measuring vertical distance from the horizontal diameter of the fan. If that point on the fan started at the 3 o'clock position, time started, and it started going counterclockwise. Okay, so how many seconds does it take for the fan to make one full rotation? Yeah, so it looks like around 2.1 seconds. And that's the period, right? The time it would take, or the interval of your independent variable that gets you one full cycle. And one full cycle is one rotation of the fan. So 2.1 seconds is the period. Okay, what's the approximate? Okay, so here's this word amplitude. So there's some terms we want to define. So this on the graph, wherever, let's start with the max. So the high point of the graph is called the max. And the low point of your graph, wherever it reaches, is called the min. Okay? Halfway between the max and the min, halfway between, in this case, is our x-axis, but it's not always. Halfway between those is called the center, the midline, or center line, but we'll go with midline. So right now the midline, what equation defines the midline? Y equals, in this case, y equals 0 is the midline. Okay, amplitude is the distance from the midline to the max, or the midline to the min. So the amplitude is like the height of the wave from the midline up to the max. That's what's called amplitude. Please. No, you just always say it's the positive. But that distance, that positive distance, is the distance between the min and the midline. Yeah, so that if you're just thinking of it as a distance, it's still a positive number, so it's the amplitude. Okay, so the midline is a horizontal line. Amplitude is then the distance up from the midline to the max or down to the min. So what's the approximate amplitude of h? 2.5 feet, which corresponds to what in our circular motion? In general. Yeah, the radius. So the amplitude is, basically, if we're talking about circular motion, the amplitude is the radius of rotation. If it's circular motion, and everything we've done so far has been. These curves model other things as well that are not in a circle. But in a if you're modeling something that's going in a circle, that amplitude will be the radius of rotation. Okay, so what I want you to do is, if the center of the fan is 4.75 feet, no more. So let's do 6.75. This is a big fan in a warehouse. Okay. 2.5 foot blades. It's up high. Okay. So the center of the fan is 6.75 feet above the ground. Now I want you to write a function that gives the vertical distance of the point above the ground. So what function would give the vertical distance of the point above the ground as a function of seconds? Can you do it? Quick, you got 1 minute. So I'm changing the question. What is the question? Yeah, so change C. So now we want the distance of that point above the ground as a function of seconds. So we'll call it F, F of t. So what are we going to multiply sine by? 2.5. Then that right there will get us distance above the horizontal diameter in feet. So how do we get the distance above the floor? Yeah, so you're just going to take all those values and add 6.75. So now the question is, what angle theta is swept in t seconds? Okay, so what value of t should get us 2 pi? 2.1 seconds. So it'll be 2 pi over 2.1. Will be that coefficient. So anything in the world that has repetitive motion, anything in the world that keeps cycling over and over again as repetitive motion can be modeled by these sine and cosine functions. And that's what we're going to do in the next couple of fast periods. See you Friday.